All right, so real quick. What is n for this first problem? 32. I love it. X bar. Somebody else, what's X bar? 68.9. Kick ass. Those are relatively simple. Part B, I'm kind of being nice. Somebody else tell me, why do we have to use, or two things you got to tell me for this. Why must we use t-scores? And sort of inherent in that is, why are we allowed to do something, period? So there's two things you have to tell me. What's the first thing I check to make sure I can even do the problem, period? What's got to be true about the distribution?
And greater than 30.
It's got to be normal. So in this case, it doesn't say it's normal, but I know I have a large enough sample size. So when I plot the means, they will be normal enough. The thing that lets me do, I could not look up the z-score that I need if I didn't know it was normal, because the z-score chart and all that does not work unless I know I have a normal curve. So that tells me I can do something, right? Hey, there's 6, you got it. Doing this here. It's a little breakdown of confidence intervals. My projector's not working. What's the second thing? What tells me, so now I know I can do something. What is it I check to see which thing I could use? Somebody who hasn't talked yet. What should be? Do you remember, what do I look at to tell, do I use a z-score or do I have to use a t-score? What is it that we look at? So if you look at the formulas, there's kind of a hint in there, right? So when do I know I can use a z-score? What's the only other difference between the two equations besides z and t? What's the other thing that's different? The standard deviation. So which standard deviation do we know? Where did the standard deviation come from that we know? From a sample. S is 3.1, sigma unknown. I really want that, that's period. T-scores were invented to cover our ass for when we don't know the actual population standard deviation. We only have an estimate of it. Right? If you just remember that, what was the purpose? Why were they invented? Not because some guy got drunk on Guinness, but because he had a sample, he could only use that. So he didn't know the population standard deviation, so he kind of created this idea of t-scores. So t-scores are used when we only know S, the sample standard deviation. So this is why we must use t-scores. And then part C, what's the degrees of freedom? 31, 11. It's always one less than the sample size. So now for part D, the very first thing I want you guys to do, so degrees of freedom is 31. I want a 98% confidence interval. What does that mean alpha is?
0.02.
0.02. So now I want you to figure out what the T is. Let's see, did I bring t-scores tables with me? Dadgummit. Alright, so who's got their T table? I think I have left all mine back.
2.040.
2.040.
040.
040?
Yeah.
Are all of you guys able to find that T-score?
I thought it was 2.453.
453, okay. So which column are we looking at? It should be two-tailed .02, right?
Yeah.
Two-tailed .02. So this definitely seems too low for me.
Oh no, he's right.
Yeah. So what is it?
2.453.
453?
Yeah.
Okay. So there's no reason you should have this memorized, but a 98% confidence interval would normally have a Z-score of 2.326. So I know the T-score should be bigger than what the Z-score would be. Yeah, so this makes more sense. I like it. And now it's just a matter of putting everything I know. We know every single bit of this equation. We know every part of it. So we know the sample mean. We know the T-score. We know the standard deviation. Where'd it go? I didn't write it down. 3.1. Sample size was 32. Can somebody tell me what this error is here?
I rounded it a little bit. 1.3440.
1.344?
Yes.
Oh, that's plenty good. Okay. Do you guys get the same thing? Let's see. Yeah, that makes sense. All right. And then, of course, you just added, subtracted. So on the quiz itself, a decent number of you guys got that first part right. You got the work mostly right, except a lot of you guys used a Z-score instead of a T-score. So it's just the fact you just take a second and you say, okay, that standard deviation I know. Where did it come from? It came from the sample. Oh shit, I gotta use T-scores. So let's see, if I subtract this, I'll get 67.556, I think. And if I add it, I'll get 70.244. Sweet. So take a minute, don't say anything, try to write the conclusion if you have enough room there. Just try to write what the conclusion would be. So on one level, so we'll do the conclusion here in a minute, but when we take a sample, I know that what I find from the sample is not the real story about the whole population. We just know that. We just know that shit. What this does is it gives a more honest answer. If I say, yeah, it's 68.9, well, okay, that's not really honest. This is a lot more honest. We are 98% confident. How's that go? We are 98% confident that what? This interval, I like it, the interval 67 point, I'm just going to round 6 inches to 70.2 inches contains what? True mean height of them. So again, what a confidence interval does is it says, okay, that number you find for the average, it's probably wrong. We know it is, because it just came from a sample. It just gives a more honest appraisal of what it looks like it is, right? And considering how small our sample size was, that's a pretty decent error, right? And it's because of the fact that the standard deviation was kind of small in the sample, so it didn't go too far away from that. Okay, maybe. So again, most of you guys were pretty good on that. You just mixed up Z and T. It's part E that got to be a lot of trouble. So in part E, ooh. So I'm almost certain you picked up when I teach, we actually kind of construct formulas together. And I understand that's not the most exciting thing, probably a little painful. I don't know. I do alternate universe Florida, all this kind of weird shit, yes? But there's a lot of idea that goes into it. Now, once it's constructed, when you see a question like how many, sample size, n. I want a formula that has n equals. That's what I want. So a few people were constructing confidence intervals on this part, on the quiz, but I didn't say to construct a confidence. I said, how many would you need? Okay, that's n, right? So which n formula would I use in this case? There's two up there, right? Obviously, which one do we have to use? You guys see the two n formulas?
T.
Yeah, the one that's got t in it, so I need. So I know what t is, 2.453. S was 3.1, and now somebody help me out. What would E be? 0.5. I love it. Now, real quick, how many men did it take to get within 1.344? It took 32 men to get the error to be within 1.134. You guys with me? So yes.
Why is it 0.5? Sorry, I got it.
So it says right here, how many men do we have to sample to be within 0.5 inches? Yeah. So that word within, it's not always going to be there, but that is a flag that's the error. I want to be within, meaning off by, meaning more or less than that much. When I had 32 dudes, we got to be within 1.344 inches. So I'm going to have to take a much larger sample to kind of make my error smaller. What I'm trying to do is, what do I have to do to be more certain about the mean I find? I have to take a bigger sample. So let's see, if you put all this stuff in your calculator, let's see what you get. 216, I don't know, it's gonna be 200 and something, I think. Yeah. 3015?
Yeah.
Nina. And you always round this up because I don't want you going and get 0.3 of a person. Don't start chopping people up. Okay. I don't want to create a bunch of little Dexters running around. Okay. I need 0.3 of you. Chop. Alright, I watched too many more movies. So I really want this to make sense. If we only take 32, a sample of 32, that's not a very big sample. My error is this big. To make my error smaller, of course I've got to take more. I've got to take 232 sample size to get my error down. Now, if I take a larger sample, I should naturally be more certain about what I see. I then have to go out less. Maybe. So if I wanted to be within half an inch, that's attainable. I can go talk to 232 people If this came out to be 232,000 people, I might go, oh shit, okay, I don't have to be within half an inch. I don't want to talk to 232,000 people. So sometimes I call this a feasibility study. How feasible is it to be within this much? Is it too many people that you need, or is it okay? All right. Then the next big thing that happened on the quiz. There's a lot of confusion apparently about p-hat. What the hell p-hat is, how to get it. And right now I just want to do a couple things here. If we talk to 111 people and 37 of them run away from us, what percentage ran away? What percentage ran away? How do you calculate that? What do you do? Don't even tell me what the answer is. Tell me what you would do. What would you do to calculate that?
37 divided by 100.
Yeah, just take 37 out of 111. In fact, we'll say it just like that. 37 out of 111 ran away. This is p-hat. P-hat is the probability of success, which in everyday language is what percent did the thing, whatever the thing is in the problem. What percentage did the thing, right? So in this case, what is it? What's 37 divided by 111? 0.33? Okay. So when you see one of these problems, and I had a few people trying to use one of these formulas here to accomplish this problem, but why does that not make sense? On the quiz, number 2, I'm not constructing a confidence interval for a mean. I'm constructing a confidence interval for a percentage. So of course I have to use the formula that's got a percentage in it, not a mean. All right, so let's look at number 2 on this handout that I just gave out today. Take a minute and figure out what p-hat is for that number 2 problem. 652 voters, not voters, registered voters is that what it was? Yeah. What? And 459 says they voted. P-hat would be just the percentage that did the thing, the percentage that voted. I don't know what that is. 5, so 0.71. What is it? 70, no. 7039? Okay, so 704. And you can use more. It has to be at least 3 places, so you can go more. Just don't go like 20 places, that's crazy. Did you guys all get that? Is that cool? So again, p-hat just means what percentage did the thing? What thing? The thing that they're talking about. In this case, voted. What percentage voted? Part divided by whole, right? Now, the next thing, some people got this, but then we're really confused about what the hell that is, right? And no matter what clothing P and Q are wearing, I don't know if you guys are cool with me saying weird shit like that. Too bad, I'm gonna continue doing it. These are both wearing hats, I don't care. What do they have to add up to be? 1, because 1 is success probably, and 1 is failure. Of course together they make 1, that's everything. So if together they make 1, how do I figure out what Q hat is? Just do 1 minus this, right? What makes him 9, what makes him 9, what makes him 10? Or do any count. Okay, I like it. So when I have a problem about means, how do I tell if it's normal enough? If it doesn't say it's normal, what do I have to look at for means? Like the first problem we did, what told us it was normal enough? And greater than 30. That's for means. For percentages, these guys have to come into play. So what is it that I check to see if it's normal enough for percentages? What do you guys remember? I have to check what? What's greater equal to 5? NP hat and NQ hat. Some of you guys are going to get this, and some of you guys aren't. It doesn't matter. If I just do this directly, what do I mean? Let me show you in a minute. If I just do N times P hat, I will bet you a lot of money you get close to this number right there. In fact, you're going to get stupid close to that number. What is 652 times 0.704? Who's got that?
459.008.
Yeah. Why the shit is it so close to this? Because how the hell did we calculate this thing? Wasn't this 459 divided by 652? So if I multiply 652 times this, I should get that. Why don't we get that exactly? Because that's rounded. So why do the work? It's just that number, right? Or it doesn't matter because it doesn't take long. But you guys see that? So what's NQ hat going to be? Here's how I do NQ hat. What's the leftover here? It'd be almost 200. It'd be 193. Is that true? I think. Yeah, 193. So it'd be 192.992 if you do 652 times 0.296. And again, it doesn't matter if you don't get it. You can just do the work here. These are both obviously bigger than or equal to 5, which means the highest bar is far enough out so that it's got room to come up and it's got room to come down. If this was 3, it wouldn't be far, it would go, that doesn't look normal. Normal should have the highest peak in the middle. Okay, so this step tells me we can do something. Let's see, did I say? Yes, thank God. I was like, did I say how confident? So why can we use z-scores? Because it's normal enough. If it wasn't normal enough, we wouldn't do shit. T-scores were invented to be used with means. Do you notice we only have one formula for confidence intervals for percentages? That kicks so much ass. Either we can do it and we use these, or we can't do it. That's it. So this says I can do it. Now I want to make the 99% confidence interval. What would alpha be in this case?
0.01.
Yeah. What would the z-score be? And you can look at your t-score chart, right? What do you guys get? Anybody? If you look at 0.01 and 2 tails, all the way at the bottom, 2.576. Again, really connect with what's happening. Why does that make sense? I want to be freaking 99% confident. I got to catch 99% of the data. I got to go way the shit out. I got to go far out from the middle. I got to go more than 2.5 steps up and down to catch 99%. That makes sense. See, now we got everything we need for this. So now we just plug and chug.
Why do you look at the t-score all the way up to 1?
So t-scores were invented to cover my ass for when I only have s, right? Is that cool? The smaller the sample, the less certain I am, the bigger the t-score gets, right? The larger the sample I have, the more certain I am that s is close to sigma. right? In fact, the larger my sample, the more certain I am about everything. So in the event that my sample gets large, the t-score becomes the z-score, because I don't need it to cover my ass more.
Oh, I know, I was asking like, why do we look at the, like, all the way at the bottom?
Yeah, because that's where the sample becomes large. What's the last row?
Large?
Large. Right, in fact, look at 2000, I think that's the one right above it.
Yeah, so at what point does it become large? Like when
And we talked about that. I love that they have the word large. When does it become large enough? It depends on how precise you need to be. Real quick, look at 2000. I think that's right above large. Is that right? What would be the t-score we would have to use if our degrees of freedom was 2000 on this problem? 2.578, right? And then the one we're actually going to use is 2.576. I mean, it already is basically the same. So if you didn't need to be as precise, how large is large? Maybe 1,000 is large enough. Go ahead and use a z-score. You don't have to be as precise. If you need to be more precise, you might actually use a t-score up to like 30,000 or something. But if my sample size is above 2,000, the t-score and the z-score are almost the same thing. They're only off by a little bit. Okay, it's a good question though. It's really weird just for this. How big? Large. What do you mean large? It's up to you, human, right? Okay.
Well, I'm sorry, I was just asking because like, it's not, if the number's under 1,000, like n is under 1,000, why don't we use the t-square that's near 1,000?
Oh, you mean for this specific problem?
Yeah, for this problem.
So what I said earlier, t-scores were, in fact, how do I check to make sure something's normal with a means, for means, n greater than 30? It's all about n, correct? Right, it's all about the sample size. So then the sample size kind of rules a lot of things. With percentages, it's all about n and p hat, n and q. It's not just about n anymore. T-scores only work with means. If this is normal enough, we use z-scores, period.
Oh, so if we're using the z-score, we just use the large one.
So if I'm doing a percentage problem, in fact, what are the 3 confidence intervals that we know? Don't we know 2 of them with X bar in it? Don't we only know 1 with p hat in it? And it's got a z-score?
Yeah.
So t-scores were invented for situations with the mean, not with percentages. Percentages, we use z-scores or nothing.
And then if we're using the z-score, we're using the score for the large sample?
Yeah, z-scores live on the t-score chart at the bottom row.
Oh, okay.
So that's kind of kick-ass because it's set up beautifully for hypothesis tests, for example, right? So if I want a z-score, I just go all the way down. So what I say with that chart is if I stop, I get a t-score. If I go all the way to the bottom, I get a z-score.
Okay.
Yeah. All right. Now we just got to plug stuff in, right? 0.704, give or take. 2.576. What was it? 652. All right. Whatever the hell that is. I don't know if anybody's trying to get ahead a little bit. And again, I love the questions. There's a lot of weird, wibbly stuff in statistics because again, the statistics is the most honest mathematics, so it's not going to be like clear cut, which is both frustrating and honest. So if anything up here that I'm doing doesn't make sense, let me know. Let's see, should I try to guess what this is going to be? 4. You really shouldn't, yeah. I guess not. 4, 35. 0.04. I think it's around 0.04, is that right?
Yeah, it's 0.046.
That's not too bad, okay. And then of course, like always, you just add, subtract. So you get what do you get? You get 6, oh crap, I have, 6, 5, 4, I think, up to 7, 5. Neato.
6, 7, 8.
6, 5, 8? Oh, yeah. Good job, Jeff. That's kind of a bigger interval, right? It's anywhere from 65, roughly 66 to 75%. But again, it's honest, you know? It's actually not that huge of an interval. An error of about 5% is not that bad. Anyway, all right, all that stuff is side notes. So we would write, we are 99% confident that the interval 65.8% to 75% contains the true percentage of people that voted, registered voters that voted. That would be what we would write as a conclusion. Okay. Another reason this was kind of like a little bit larger of an interval is because we went out really far. We made it 99% confident. I gotta go out much further to be that confident. Okay. So hopefully that cleared up some things, I don't know. Hopefully that cleared up a few things. So if you came in after I said this, I didn't curve this quiz, but I am gonna do something, so that it doesn't count as much in the overall quiz grade, because again, the grades are pretty low. Yeah? Oh, you good?
Oh,
Okay, so. It's kind of, I wish I could say that I did this on purpose, but this is gonna lead right into what we're doing today, which is more hypothesis tests, like crazy amounts of hypothesis tests. But now we're gonna do one for percentages, right? So we're gonna create a hypothesis test for a percentage. So for example, if I thought that, more than 60% of stats students pass stats, then I would have to test that claim, but that claim is about a percentage, right? Okay. So let's do this. There's going to be 2 places where things change compared to hypothesis tests for means. So if I look at, why am I using you? Sorry, little marker dude. Hypothesis tests for means. Let's look at for means. Just real quick. I'd have an H0 and an HA with mu in it. Blah, 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 blah. Yes? So if I'm doing it for percentages, I'm going to have a H0 and an HA with P in it. Blah, 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 blah. Okay, that makes sense, because we're talking about percentages, not means. The second step was, is it normal enough? And do we use Z or T? All that kind of stuff, right? So this had to be N greater than 30, and then we looked at, is it sigma or S? How do I tell if a percentage problem is normal enough? We just did it. What do I have to check? Yeah. Now, the funny thing with hypothesis tests, we assume we know what P is, so we don't have to use the hat. We don't have to use the sample one. We actually are assuming we know the real percentage. Okay, so this makes sense. All the steps are the same. It's just that some of the steps are going to be different because I'm talking about percentages, not means. But I still have to check if it's normal enough. I still have to set up my hypotheses. Third step was critical region, or what I call rejection region. You call it that. This is exactly the same. Same. Next step was, now here's the huge difference. The next step was to calculate Z star, which used to be doing this. Right, we would calculate the new standard deviation, then we would create a z-score from that. So here, I still have to figure out how far away my sample gets to see if it got far enough away. But obviously I can't use this formula because I'm not talking about means. So instead, I really want, do you see how this is my sample mean and it's all about how far away it gets from the supposed mean, right? That's what this is all about. Did I get far enough away? So here I'm gonna have a sample percentage and I wanna see, did I get far enough away from the claimed percentage? Okay. Now what goes on the bottom here is the standard deviation for sample means, right? For percentages, what we're gonna do, this is kind of nice, this worked out this way. Do you see how right here, that is this, correct? You with me? Okay. More rain, sounds like. Do I have anything in you? Are you still alive, sort of? Okay. What's in the same place in the percentage equation? Well, this is. That is the standard deviation. I want that to make sense. The mean, give or take, z times standard deviation. The percentage, give or take, z times standard deviation. This is the standard deviation for percentage samples. Just like this is the standard deviation for mean, sample means, right? Okay, maybe. So this formula is going to have that thing in it. One little difference, we don't have to use the hatted ones because we're assuming we know this is the real percentage. So why did we have to use the hats here? Because I don't have a clue what the hell P is. I don't know what the hell it is when I'm making a confidence interval. Here, we're assuming we know what P is. It's whatever the hell they claim it to be. And we're going to go, assuming you're right, let's try to do something weird. And then, of course, the fifth step is exactly the same. You reject the null, or you fail to reject the null, all that kind of stuff. Okay, maybe. So exactly the same 5 steps. I still have to set up my hypotheses. I still have to say, is it normal enough? I still have to set up a rejection region. I still have to calculate where my sample fell. I just obviously use percentage stuff when I'm talking about percentages. So let's try a problem. Let's see. Yeah. Can I change this one? Yeah. Blah, 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 blah. Okay, good. Oh, sorry. Sophia. Okay. So, hypothesis test, 5 steps. Definitely not students' favorite thing. But thank God that when I'm talking about percentages instead of means, the 5 steps pretty much are the same exact thing. There's nothing brand new. There's just some different formulas to use for some of the steps. So read through this. All right, so can somebody tell me in Mathish, right? Actually, tell me in English first. In English, what's the claim that somebody's making? Anybody? Oh, go ahead.
It's that the Chicago residents have 55%, unfavorable view of the buildings.
Okay, and we could be a little more specific, at most 55%, right? Okay, now can we convert that statement into a purely mathish statement? Because again, I like to tell my algebra students, you know, math is hard because it's a different language. So the claim is the percentage of people with an unfavorable view is at most 55%. So the percentage is at most 55%. What symbol represents at most?
Greater 8%.
If you could have at most 10 people in an elevator, what does that mean? Less than or equal to, right? So it's kind of weird. We hear most and we think more and we think greater than, but at most means that or less.
Question. How can we determine which use of the equal sign and not to use the equal sign, but the less than greater?
So if I would have said that the claim is they think it's less than, that would not include an equal sign. If I say it's at most, that means it could be equal to, right? So at least, at most, they both have an equal
So
sign.
when we see at, pretty much it's.
At least or at most,
Okay.
that would have an equal sign, yeah. Okay. Any hypothesis test I give you, your very first step is just write the claim in Mathish. How do you know where it goes? Which one of these does it go in for? And I might have put an H1 yet. Oh well. An older book had ones in it, but oh well. It's a little ha. So it used to be the hos and the highs. In this book it's the hos and the ha's. Which one does that statement go into? What does the ho have to have? What's the null hypothesis have to have in it? Equal sign. Does that statement have an equal sign? So it's got to go here. So what's the ha going to be? What's the opposite of this?
Less.
No. Less than is part of what this says.
Oh,
What does this guy leave out? Everything that is bigger. Basically, if one of your parts has an arrow, the other one has to have the opposite arrow so that it picks up everything, right? Is this going to be a one or a two-tailed test? One tail. In fact, can you be specific? Which side is that tail on? Left or right? Good. This is the one we can show evidence for. Always. This guy sets up where the rejection region is. I can't show evidence for this because it allows it to be equal to. A sample can never show evidence that something equals something. But it can show evidence that looks like something's not equal to something. So my rejection region is going to be up there. So the alternate hypothesis always sets up where the rejection region is and how many tails it's going to have. Okay. So now, is it normal enough is the question. I can't remember how I put it. Can we use z-scores as I always said? Yeah, I said, is it normal enough? Beautiful. What do you have to check to see if it's normal enough?
Number is greater than 30.
Nope. NP and NQ, yeah. What is N in this problem? 996. And we are assuming we know what the percentage is. We're assuming that this is the actual percentage. And we're trying to show evidence that it isn't. So 0.5. So in a court case, don't tell me the reality of like the court of public opinion, but in a court case, officially, what do you assume about the person on trial? What do you assume is true? What do we assume is true? What's supposed to be assumed true if somebody's accused of something? We assume that they are innocent, right? That's what we're supposed to, correct? Do we? If somebody's like, they catch it, you're like, that guy's guilty. But we're supposed to assume somebody is innocent. And then what does the prosecution try to do? Find evidence that he's not innocent. We always try to find evidence against the null hypothesis. So we try to find evidence for this guy. I'm not sure where the case came from. I don't know where. Okay. But so, here's where it came from. So we're assuming it is 55%, and then this whole process to try to show evidence that it isn't. We're trying to find a contradiction. So assuming that P really is 0.55, what would Q be?
42.
Good, 4.5. So I always got to make one with P and Q. So help me out. What is that? Like 547 point blah blah blah. That's at least 5, and this is going to be 449 blah blah blah, and that's at least 5. I believe. I believe. I believe. Roughly, okay. So this is exactly the same as n greater than 30. It's exactly accomplished is the exact same thing. It's just n greater than 30 is for means, and I have percentages. I am sort of, it doesn't matter. Part C, which I'm calling 3. Let me do this real quick. I guess. Yeah, I did do this right. A, and then I just called this 2. That was a good job. Okay. Now I got to set up what that rejection region is. And this step says, what's enough evidence going to be? How much evidence do you have to show me? So in an actual court case, it isn't quite clear. We just say within a reasonable doubt. This is a little more precise. So what does this mean? What am I allowed to use? The fact that there is normal enough. What can we use? Z-scores. In this case, what is alpha? Can you guys see what alpha is? 0.005. I'm trying to remember. Yeah, I think this should work. Is it a 1 or a 2 tail test? 1 tail. Can you guys find what the z-score would be for that? So 1 tail, 0.005 z-score, right? So you can look at your t-score chart, because the z-scores live at the bottom.
2.576.
Yeah, and do you guys, the t-score chart is just set up beautiful for a hypothesis test. Got a 1 tail hypothesis test or a 2 tail, so I know exactly where to look, and then it just kind of stop if I want a t-score, don't stop if I want a z-score. So 2.576. What this means is any sample we take to show evidence for this guy has to be at least that far away from the mean. Because again, if I take a sample, will I get the actual percentage from the sample? Hell no. So it's automatically going to be different. This says in order to be evidence that the real percentage is different, you got to be really different. You got to be that many steps above. That's where evidence starts. So now, of course, it makes sense. We just set up what far enough away is. Let's go see how far away we got. Can you guys tell me from the sample, what is p hat? How do you calculate p hat for the sample?
594 divided by 96.
Yeah, 594 of them out of 996. I think it should be like 596 or something, maybe 5?
Yeah.
Is it 6?
596.
Okay. So in step D, I'm kind of nice. I'm kind of telling you what to get. What is n? Well, we know n, that's easy. 996. What is, and x doesn't matter. X is really just the 594. So sort of helping you put this together. Do you have everything you need for the Z-star now? Where's the only place in the Z-star formula that this goes? There's only one place for this guy. You guys see what I'm saying? This guy, he only goes in one place, the very beginning. Everything else is P and Q, these guys, right? This is P, and this is Q. So I got our data minus what we're checking it against, divided by square root of P times Q over N. Let's see. 1.5 over 10 squared root of 10, which is like 30. 6.16, so 0.016. 0.16 is 2.9 something. I don't know, trying to get in my head. Gosh, I gotta stop doing that. I gotta stop doing that. I think it's 2.9 something. I could really be wrong. You have to be really careful about putting this in your calculator. Oh, holy shit. Anybody feel brave?
2.9.
Yeah. I like it. I give myself a little props. It's not bad. It's 2.9. It's pretty good. All right, I'll stop. It's my one skill. Did we make it far enough away?
Yeah.
So here's what the cop thinks. The cop thinks it's at most 55%. We got a sample that was way the hell up here. That is evidence that this guy is wrong. If this guy was right, where should our sample have shown up? It should have shown up in here somewhere. But we showed up way the hell up there. That is evidence that this guy is wrong. So right here I can write reject the null, support the hop. That's what this does. If we don't make it in there, then we fail to reject the null. We fail to support the hop. Which one was the claim? The hook was the claim. So which language do I want to use? That language. That's it. That's it. There's nothing, there's no guessing. There's no, oh God, let me just pick one. What word does he want me to use? No, we got to talk about the claim, and we just rejected the claim that this cop made, right? So our conclusion, we have found sufficient evidence. This is how I write sufficient evidence to reject the claim that plagiarized 55% of Chicago residents, at most 55% of Chicago residents have an unfavorable view of police. Cups. They have an unfavorable view of cups. They don't like cups. Or maybe it's cups. I don't know. There's one little thing on here that I haven't talked about yet. Do you guys see on step D, sorry, step 4, where it's got in bold, find the p-value? Okay, we haven't talked about that yet. What's the alpha? Can anyone please identify on this picture I've drawn, how could you identify to me what alpha is? Where is alpha on that picture?
Maybe on stuff
Say again?
or maybe stuff in the month.
No. What did alpha help us do? Didn't alpha helped us look up this number here, right? Why? Just tell me, in general, what is alpha? Alpha, fish. It looks like a fish. What do fish have on their back end? Tails. Okay, so what does alpha tell me? So this is kind of funny because alpha is the Greek letter A. Cool? Looks like a fish that has a tail. So what does alpha tell me? Area in the tail or tails. It's kind of neat that the symbol is basically saying, hey, I'm A, and I got a tail. Okay, area in the tail or tails. So up here, where is alpha? Alpha is that little squiggle. Alpha is this area right there. That is alpha. It's the area in the tail that this z-score makes. P-value is the area in the tail that our z-score makes. So this picture kind of sucks for this, but here's our z-score, right? 2.92. This is an old kind of question, but can anyone please tell me what's the area in the tail for 2.92? You guys looked it up. You got to do it old school. You got to look at your z-score chart, right? What's the area in the tail of our z-score? That's what the p-value is. You got to be careful. Look up 2.92. You get the area that's on the wrong side, yes? You have to kind of adjust it. So what do you get when you look up 2.92?
0.0.
Well, no, 0. No, when you look up 2.92.
On the negative side, right?
That's the shortcut.
Yeah.
So I got you. If you know the shortcut, use it. But if you look up 2.92, what do you get? Anybody?
On the non-shortcut, it's 99.82.
All right. So 99.82. So this is 99.82. So the area in the tail is 0.0018, which is what you got when you use the shortcut, right? Okay. The probability that we would get a sample where we did, if this is a correct statement, is 0.18%. Let me say this again. There's a 0.18% chance that we would have gotten the sample where we did if that is correct. Do you understand? Based on where we just found our sample, there's only a 0.18% chance this is correct. Therefore, this is more likely correct. Do you guys agree? That's why I can reject this dude. Am I 100% certain that that guy's wrong? Could that cop be right? Oh, hell yes. Because we just took a sample, and our sample could be skewed one way or the other, right? Maybe we talk to our friends, in which case they agree with us. Okay, maybe. I'm not trying to assume how you feel about cops. But, I don't know. It's getting a little hard nowadays. Okay.
Quick question.
Yeah.
For the percentage, like this one, you don't need to find the ZF, degrees of freedom.
Beautiful. You'll notice something really nice with percentages. As long as this is true, you use z-scores. If this wasn't true, you don't do a damn thing.
Got it.
You never use t-scores with the NPQ problem, with the percentage problem.
And then for the p-value, it's 0.08.
Yeah, that would be
Okay.
0.0018. I like it. So the acceptable probability was 0.005. We got something even lower than that. That's another way to kind of see if we reject the null. is to just look at the p-value. Okay, let's do this. Let's talk about types of error, and then we'll head out a little early. I get a feeling we're a little wiped out on hypothesis tests. I understand. We need to do enough so you kind of see how they go. This has got a couple of differences, but it's basically the exact same flow. So let's do one example, one concrete example of the types of error. We talked about type 1 error, type 2 error, but we did it kind of quickly. So let's use the example I gave earlier about a court case. Let's say somebody's on trial for murder. What would our null hypothesis be? What do we go in assuming is true? We assume they're innocent, right? Innocent until proven guilty, correct? Now again, I'm not talking about the public watching this on TV, because people are like, oh, you did it, Well, officially in the court, you have to assume innocence. It's up to the prosecution to show enough evidence to say that he's guilty, right? Or she, all right. So this is going to be words. This is kind of awesome. The null hypothesis is innocent. The word innocent is so weird. So what's the alternate hypothesis? Guilty. A type 1 error. The definition of type 1 error is reject a true null. So the way I remember it is the shorter phrase. The other one is fail to reject a false null. Reject a true null. That's type 1. I don't care too much if you memorize that. I'm not gonna, but you have to understand what the possible errors are. So what does this mean? What's the truth? If I made a type 1 error, if we go through this trial and we ended up making a type 1 error, what actually happened? So in a type 1 error, what is the truth? Which one of these is actually true in a type 1 error? It tells you. What's true? True? No. So what's true? What's true is they're innocent, right? The null is true. So in reality, they are innocent, but we think what? But we say they're guilty. So in this case, what could happen? If you're on trial for murder and you're found guilty, what could we as a society end up doing? What's more than likely going to happen to you if you've committed murder and we are found guilty? Go to prison for damn sure. But what could happen to you? Go to death row and eventually we kill you, right? So in that case, is that bad outcome? What have we just done then? We said they were guilty, but we were wrong. They're actually innocent, and they go to death row and they get killed. We have just killed an innocent person, correct? And don't start to get all freaky. I'm not trying to impose on you any viewpoints. That's just the reality, correct? And some people can argue, well, that's just the price of having a safe whatever. I'm not here to argue any of that. You with me? Okay. I have a hard time keeping my true beliefs to myself, but that's not part of what I'm here for. We're just here to talk about the realities. Type 2 error. So that's pretty damn bad, correct? An innocent person put to death is a bad outcome, I would say. What would a type 2 error mean? So the official definition is fail to reject a false null. So what you can always start with is the reality is the null is false. So that means what in reality what? In reality, they are guilty, right? This is false. In reality, they are guilty. But we think what? We think they're innocent. I can think of many a court case in recent past where this has happened. Some could argue this is not as bad of a result because at least we didn't kill somebody who was innocent, but at the same time, somebody goes free, that should have been punished, correct? You guys all with me? Does that make sense? So let me give you one last example. Let's say something less interesting. Let's say that the null is that the mean is less than or equal to 11, and the alternate is the mean is greater than 11. So what would a type 1 error be? Reject a true null. In reality, the mean is at most 11, right? Reject a true null. So the null is real, is true, but we think the mean is greater than 11. That's a little bit more boring of a situation, but it's more like what we're going to see in our work, right? So a type 1 error is the null is true. This is the reality, but we think this is true. We rejected a true null. Type 2 would just be, in reality, the mean is greater than 11, but we think the mean is less than or equal to 11. Okay. And again, you could do a hypothesis test perfectly correct. You could do all the calculations perfect. Nothing wrong with what you did at all, and your result could still be wrong. Because if a murder happens, are we ever really 100% certain about a person's innocence or guilt? Very rarely, right? Unless it happens in the court, on TV, and everybody saw it. Even then you're like, were they wearing one of those freaking masks and looking like somebody else? Is this AI? Oh shit, But oh well. That's the reasonable doubt part. Okay. Oh yeah. Okay. So again, I want to go to I want you to understand types of errors. The types of errors are not the big, huge, important part of this, but I want you to understand them. They're not that freaky. Is my hope. Okay. All right. So now we got to a point where you should be able to do every problem in chapter 9, or at least attempt it. There's nothing in chapter 9 we haven't talked about. We still have to do, on the other side is another example, but we'll do that next time. I think we deserve maybe a bit of an early ending to the class. Just to remind you guys, I am in this room half an hour before the class starts. I'm in the Math Study Center a lot. There's tutors that can help. So if you're not where you want to be, and there are things you haven't been doing, start doing those things and you'll get to a better place. So just let me know. All right. Thanks, guys. I was worried for